1 second. I'm just going to say a couple things first. Okay?
Oh. Intro man.
I just want to say a couple things first. Cool. Okay, so welcome to our second to last Lunch and Learn in the summer. This is pretty exciting. I think this is the most packed room we've ever been. So I think a lot of you understand that we're talking about a couple of exciting new technologies today, but are hopefully going to be making an appearance at the HCBI pretty soon. So for those of you who don't know, Chris is going to talk to us about the Elira 7 today, which is a new super resolution system that Zeiss has just released. Ours is on its way from Germany. We believe it is now in North America, hopefully in New York, and it's going to be making its way up here shortly. So we're hoping within a couple weeks, the system's going to be installed and set up in a room across the hall from the HCBI, and we're going to be able to start demoing it, trying it out, and having you folks bring some sample slides to take a look at it. So keep an eye out for some emails about that. Like I said, it's probably still going to be September, week or two into September before we really get rolling with it. But keep an eye out for that, and if you have questions, stop by and let us know. Okay? So other than that, I'm going to hand it over to our embedded Zeiss specialist, Chris, who he was actually intimately involved with the development of the system in Germany before he came here. So he knows this thing inside and out, and he's going to give us a great talk about it today.
Thanks, Fred. I used to know it inside out. Hell knows what happened since I got here. Hopefully not much because it's really good. Okay, we have a kind of a full program today. I'm not going to talk so much about all the formidable options that you have available on the Elira as a commercial product. I will focus more on what you can do with it and explain a little bit the underlying technology behind it. How do you accomplish super resolution? And it's important to understand that once using the system, to know what's behind the makings of generating beautiful images. That helps in the sense of preparing samples the proper way and so on and so forth. So we have quite a program today. We'll take some look at some pretty images. We'll look at the equipment, but we will also take a look at some of the working mechanisms behind it. And there will also be audience participation time further down the road. We will need a couple of volunteers so that you already prepare yourselves mentally. Maybe 5 or so volunteers. I will tell you when it's time to do the audience participation time. Okay, before we even start with the nitty-gritty, the technology behind it, I wanted to start right off with some pretty images. What you see here is a meshwork of tubulin, and the moving patterns you see there, the little orange moving patterns you see there crawling up and down this tubulin meshwork. This is the end-binding protein that attaches to the tubulin and makes it grow into one direction. And to get a better look what super resolution brings to the table, you take a look at the image to the right side here. The distance between these two little green dots here is around 120 nanometers or so. So this is the same movie. It didn't have to be zoomed in or cropped or anything like that. It's the same movie. It's just I think I cropped that part out here or there, but it's that little part up here that is zoomed in. Really get an impression what super resolution is bringing. Of course, super resolution on the Elira system is also capable of generating sets of 3D data. What you see here is one of these things that used to be, I don't know, some of you have had some exposure to super resolution microscopy and structured illumination microscopy, is that, you cannot go very deep into the samples. Well, now with the new lattice pattern, you can go substantially deeper, as long as the sample is transparent, obviously, or translucent. What we see here are neurons stained with GFP. You can go 75 microns deep into the tissue. The field of view itself is 75 by 75 microns. So what you see there is a cube of brain, and you can then zoom into the individual neurons and make out little spines, neuronal spines. Okay, so now we have seen pretty images. Now let's see little uglier images. Resolution. What is resolution all about? Why resolution? What is this thing? Why super resolution? Resolution is the act of processing something into its constituent parts of elements, the smallest distinguishable unit of measurements, blah, blah, blah. We sort of understand what resolution is, but we have to be reminded constantly that resolution is not just XYZ resolution. It's not just the stuff that I can see in space, like the tiny details or the smaller pixels on the camera. But resolution also has other aspects, like there is time resolution, there is spectral resolution, there is chemical resolution, there is all types of resolutions that play a role here. And we will focus a little bit on these aspects of resolution. And speaking of resolution, axial and lateral resolution, the best resolution can be achieved hands down with an electron microscope, right? Nanometer resolution is commonplace. You can zoom in and zoom in and zoom in and zoom in, and you can resolve down to the individual synapse in a chunk of brain. It brings a few problems. So if you judge the technology only by the merit of its resolution, electron microscopy is hands down the best. It goes down to the nanometers, easy. Optical microscopy reaches sub-micron scale. That's the Achilles heel of optical microscopy. But if we take a look at some other aspects of these two technologies, so the electron microscopy is limited to a surface, it's slow, it needs usually heavy metal contrast agents, it needs to be fixed and dead specimens, it has poor chemical contrast, it has relatively high maintenance. These are the Achilles heels of an electron microscope. Optical microscopy, in contrast, is minimally invasive. It gives you access to the sample volume. It's completely compatible with in vivo conditions, so I can take a look at living specimens. It provides chemical contrast by virtue of fluorescence labeling, and it's relatively simple, fast. In fact, it doesn't even require electricity, right? This was invented in the 1600s or something like that. So, the Achilles heel of optical microscopy is this little bit here. But before we go there, let's take a look at these other statements. So if you compare the electron micrograph to the left here with its magnificent nanometer scale resolution and an optical fluorescence microscopy image to the right side, we can see here the distinguishability between individual compartments of the cell because they're expressing different things. On an electron micrograph, I have not straightforward the possibility to ascertain whether this little dot here is a specific protein that is interesting for me, that is interacting with another protein that is in this little white part that is interesting for me. I do not have this capability. If I have a white pixel in a sea of other white pixels, or a black pixel in a sea of other black pixels, I do not have this kind of contrast. And this is what fluorescence brings to the table. This was a tremendous boost for optical microscopy. It started in the 50s, and then with the possibility to genetically encode GFP and things like that. In the 80s and 90s, fluorescence microscopy is the method of choice for chemical contrast. Okay, so in optical microscopy, the Holy Grail, or the place where all attention is concentrated, is its Achilles heel. It's the trying to overcome this micron scale resolution here, and this is what needs to improve in optical microscopy, and this is why recently we had this boost, and this is why you have the so-called super resolution optical microscopy. So we have to understand then also what does resolution mean optically. This is Ernst Abbe, who paved the way for the calculations of optical resolution and things like that, is using actually very, very advanced for this time, wave equations for light. Remember, this was 1900, before 1905. People didn't even know light are waves or particles. They seem to behave in both ways. So early on, he adhered to these calculations, and he figured out roughly that the smallest distance between objects, between two objects that you want to optically resolve, depends on the wavelength that you're using. The shorter the wavelength, the sharper the object is going to be that you can resolve, divided by roughly twice the numerical aperture, which is the angle, the exit angle of the objective lens, which is give or take 1-ish. So if you want to have a rule of thumb calculation for the best resolution you can obtain, you take the wavelength you're detecting and you divide it by 2, more or less. So if you're detecting 500 nanometers, we'll probably have a resolution of 250 or so nanometers. Theoretically best. Usually it's even a little bit worse. 270 nanometers, something like that. Okay, so technologies, developments that surpass this limit, which is it's not a solid limit, right? There are ways to circumvent this. They're collectively called super resolution techniques. There are plenty of those around. Here is a little chart for comparison. Also, if you take a look at the booklets that were lying up there, they sort of explain in very rough terms, in a very beginner's manual kind of way, what these techniques bring to the table. So starting here, you have an axis that increases with the resolution, lateral resolution from right to left. A confocal microscope could be seen as already a microscope that allows to go into super resolution realms. If you close the pinhole small enough, you get to a square root of 2 improvement over the resolution limit. So the confocal instrument itself is already kind of a super resolution technology. If you couple that with deconvolution techniques, you will get to a ballpark of 180, 200 or so nanometers. It has some, I will not read through all of this table, it has some advantages and disadvantages. The advantage is it's very simple. Confocal instruments are ubiquitous. You'll find them in many places, and performing a deconvolution is computationally cheap nowadays. However, you need high quantities of light shining down on your specimen, and that might lead to phototoxicity, photobleaching, and so forth. We have launched a couple of years ago the ARIScan, which is a super resolution detector in the realm of confocal imaging that does away with the wasting of light, but at the same time closing down the pinhole. Also coupled with the convolution, you reach down to 120 nanometers resolution there, all with its pros and cons. SIM, Structured Illumination Microscopy, works with standard samples. It's suitable for in vivo studies. It works not by closing down the pinhole, but it works by modulating light and shining a structured illumination onto the sample. And we will see further down in the next slides how this is accomplished. But again, here you're in this 100 plus X nanometer ballpark here. There is STED, which operates like a confocal microscope. Oops. However, you have the depletion beam around. It's like a pencil sharpener. You will have an area around the confocal beam. If you know what the confocal does, it will explore one region in a raster scanned way, and then it will scan another line and another line. And the sharper this tip is, the more precise you can collect an image. And instead does that by applying a donut of light around the big tip of light, making it sharper. In hand waving terms, this is what it is, but it requires very high laser powers in order to achieve that sharpening. Finally, there is localization microscopy, single molecule localization microscopy, where I can pinpoint individual molecules, and then by understanding where the individual molecules were, infer from their positions how the bigger object looked like. And we will focus on these two techniques, structured illumination microscopy and localization microscopy, which are subsumed together. They are built into the LIRO system, and we will first focus on structured illumination microscopy, and then we will take a look at localization microscopy, these modalities of super resolution microscopy. in a nutshell, what you have here on the left side, on the top image, is a diffraction limited, the Ernst Abbe diffraction limited image of tubules with the smallest distance between two tubules. Here, these two, for example, of 240 nanometers. If you apply a structured illumination that is sort of depicted down here, and we will see what this is in detail a little bit later on, you can reconstruct an image with an extended optical support function, which is shown here, and we will understand that also a little bit later on, and reconstruct an image where the resolution can be doubled to 120 nanometers. So now you can appreciate that this is not one fiber, but actually two fibers lying side by side. On the right side, there is the other form of super resolution microscopy, which I hope there used to be a little video down there. What you see here is the switching on and off, the stochastic switching on and off of individual molecules as they appear and they disappear as I'm shining light on them and running a film to acquire them. And I can pinpoint the positions of the individual molecules that showed up in this image and map those down here to about 20 nanometer or better resolution and reconstruct the image and appreciate details that were not available before. Okay, that would be the comparison. Here's the total image with all molecules on, and down here, if you take a look at this area here, for example, you can appreciate, you can disentangle all the individual molecules on there. We will see better examples a little bit later on. Okay, so we begin with structured illumination microscopy. Structured illumination microscopy is a very, very old trick. This is a picture of Baron-Rayleigh, of the Rayleigh criterion, the distinguishability between two objects. One of the things he was famous for, he was looking at spectra of stars and of celestial objects, and he was passing those through a grating and looking at the spectrum of these things. And one day he came to one of his students and he said, hey, I would like you to manufacture a grid for me on a glass with a little diamond needle with 3,000 grooves per inch or something like that. And the student went there and he carved those grooves into this piece of glass, gave it to Mr. Rayleigh. Mr. Rayleigh, of course, does not trust his student, took it to a microscope, tried to look at it, but this pattern was way smaller than what the objective could resolve. 3,000 dots per inch was nothing that Baron-Rayleigh's microscope was able to resolve back then. But he was a very smart man, so he took a grid that he had manufactured before, of which he knew the grating constant, and he overlapped the two. Funny little glitch. I have a white screen here. And this one is not going further. Okay, okay, now I have the white screen over there as well. I will start this thing with a little easier. Okay, so let this slide me the 12 or so. We are and boom. Okay, so now it even works. Yeah. So what he did, he overlaid the two, and what he noticed then is that there is a beat frequency between the two underlying frequencies that could be measured And if you work out the maths between the grating number 1 and the grating number 2 are interacting at a given angle and producing that moire fringe or that beat frequency, you can work out what the other frequency is. And by doing that, you figured out that the student actually indeed did the 3,000 dots per inch, so we'll wait for the student. And in mathematical terms, what they're doing here is the product of two sine waves, if you will, that lead to higher harmonics, and those can be analyzed and then to resolve the frequency that cannot be resolved by the optical instrument. To cut a long story short, let me demonstrate this for you using images. But before we go there, we have to understand a little bit what Fourier transforms are. Just it might be in the back of your head, but this is Mr. Fourier here. He had dyspepsia, and he was a very weird kid. He did not, this was around the time of the French Revolution, where there was revolutionary French people, and switch this off. But he was somehow in his room more concerned with mathematics than with playing war with his little colleague. What he came up with was that you can take any curve, any arbitrary curve, like this ratchet curve here, and you can decompose it into its individual frequencies. And you can also take all these frequencies and sum them up and recompose this ratchet curve down here. So you can take anything in real space and transform it into frequency space, and take anything in frequency space and transform it into real space, and vice versa. Mathematically, what happens is this, is the function in frequency space is the function in real space multiplied with a sine wave of different frequencies in dependency of its frequency. So this object here has similarity with a sine wave of this frequency, with a negative sine wave of this frequency, and so on, summed up by all its amplitudes. And if you sum all these sine waves up again, you obtain the same image in space. So you can go back and forth between frequencies and real space objects. How does that look like in images, I hear you ask? So this is an image of a computer, Fourier transformed, and this is the Fourier transform here. Of this image, you have right in the middle, you have very low frequency objects, and down to the periphery of that, you have very high frequency objects. And if you back Fourier transform this image, you obtain, so if you take this into image J and you press an inverse Fourier transform button, this here comes out. Yeah? And what can you do with this? Yeah, well, you can ask, for example, okay, so how would the image look like if I suppressed everything else and reconstructed only the stuff that is here in the middle, only the low frequencies? You're left with, something like this big area here where this oscilloscope is, will be returned over here. The big dark ceiling here is a big area, because you have a big dark object over here, but you will not see the individual the little wires dangling from the top here, or the individual knobs of this object. They're too small. They fall outside of this low frequency. They would be over here. You cannot see them in this image. What if I expand the radius? Well, as I expand the radius, I get sharper and sharper images. I can also devise crazy filters like, well, okay, let's get rid of everything that is blurry and keep only the sharp stuff, right? I would omit the objects that are blurry and keep only the sharp stuff. And what I have created in this way is an edge detection algorithm that is, every iPhone has that, right? It's the stuff that the police may not use in Cambridge anymore, right? For facial recognition and stuff like that, is they do this edge. So the distance between your nostrils, between the pupils of your eyes and things like that are high frequency elements that are over here in space. And you can, with Fourier analysis, take a look at it. So let's take a look how gratings behave in space. So the smaller the grating is, the farther apart the points will be in Fourier space. And if they are tilted with an angle, I will see also the tilt in the angle over there. So this is for sine waves, what happens. And one question that I like to ask the students is, why are there 3 peaks in this Fourier transform if I only have one frequency? The answer is, I have a middle frequency here because this sine wave does not go negative. It goes from 0 to the 255 or something like that, and it goes back to 0 and 255 and so on. And its mean value is not 0, like a sine wave would have a mean value of 0. Because it's not 0, you have a peak there in the middle. The other 2 points, the plus and the minus, they are always the positive and the negative. I don't know in which direction this wave is going. It doesn't matter if the wave is going from left to right or from right to left. So it will always have a point symmetric function down there. At any rate, if I have an objective that has a, this objective here, for example, would not be able to resolve objects that are smaller than this grating, then I could draw a circle around the maximum frequency that is allowed to be captured, and that is exactly what happens at the back aperture of an objective. This here, if I take an objective and I look at it from the back side, this ring here is more or less the size of the frequency space in Fourier space. And if I make this larger, I can resolve finer objects. If I make this smaller, I cannot resolve smaller objects. Okay, the next ingredient we need to figure out is if I take 2 gratings and I overlap them, right? I want to play so Baron Raleigh and overlap gratings. So I have options to overlay the gratings, just summing them up over here, and then I will say, well, I have the middle point here, and I have the original grating here from left to right. This is F1, and I have the F2 is a slightly tilted. I will have the points here and there, but I don't have anything additional to that. That's all the information I have. I have the grating 1 and grating 2, like in the sum, 1 and another 1. If I make a product of the 2, if I multiply the 2, well, suddenly things look a lot stranger, a lot different. I get cross terms. I get this additional point here and that additional point there. And the first people to figure that one out were the people around Aristotle and around the turn of the 1st century before Christ. And this is basic trigonometry. If I multiply sine of theta and the sine of phi, what I end up with is the result is half the cosine of the difference minus half the cosine of the sum frequency. And if I look at it in Fourier space, all it becomes vector addition. So I have the original grating over here and another grating over there. And the sum frequency, this red term here, is the sum of this vector with this vector, so I get this point over here. The difference frequency is also a vector where it's this vector minus the other vector, and I get the point over there. Okay, now we can use this to do some very interesting tricks. We can use this to double the frequency of stuff that we can resolve. Bear with me. Okay, this is resolvable grating number 1, resolvable grating number 2. Everything adds up. If I multiply them, I get this frequency over there. If I make this one grating here smaller so that my microscope cannot resolve it, I will get a different spot over here. Now I cannot see this spot, I cannot see that spot, but I do see this one here. And what I want is actually I want to resolve this vector here. I want to take this point and actually put it over there. So how do I do that? Well, it's very simple. I have this point, I know what my grating is, so all I have to do is I have to shift the tip of this vector by that much grating in that direction, stitch the image together, inverse Fourier transform it, and obtain my image. Right? Okay, it works in theory, but I see a big question mark hovering over all your heads here, and I strongly encourage you to do this experiment using papers and scissors and ImageJ, right? And here you can play the following game. Here on the left side, we play an omniscient demiurgus or something like that that knows everything. And on the right side is the human universe that is limited and whatnot. I have here a grating, another grating. I have the product of these gratings, and I have the Fourier transforms of those. And then this demiurge plays a trick on the humans, and he says, well, okay, your optics are going to be limited to this green circle, and this is what you give to the human side, and the humans would see this. If you inverse Fourier transform this image, this is what you get. So you don't get nice stripes, you get some kind of weird thing there. This one you can resolve all right, and this product looks a little bit weird like over there. So what we would like to do now is forget all the instructions and start from this point. Well, this is all the images I get. Yeah, I know what my grating was. Okay, this is also okay. And I'm allowed to Fourier transform stuff. And I would like to take these three ingredients and end up over here. So I strongly encourage you to do that, what follows in image J. Okay, so you take the image of the Fourier transform in image J. You go in there with little scissors. First of all, you find out where the grating peak is. It's 10 pixels to the left and 10 pixels to the right. You cut out everything that is not in this axis, and you move it. You cut it out and you move it by 10 pixels to the right, and you move it 10 pixels to the left here and to the right over there. And then you remove the grating. You go in there with an eraser, and you remove the grating and everything that is vertical to that grating. And now you take that thing and you inverse Fourier transform. Okay? When I saw this, it was clear to me, well, okay, this stuff is not just in Gustafsson's paper, right? It actually does work. And I strongly encourage every one of you to do that. What we need now, and this is basically the super resolution. And we need now this to be done in a reliable and automated way for an arbitrary structure, for a microtubule network or something like that, using software algorithms. Okay, and this is what is written in Gustafsson's paper from 2000. So we understand now, maybe some of you have seen these petals, this nice looking shape of, how the optical transform function increases to the side, and the frequency that was here is now doubled over here, so I can resolve structures that are twice as large. Okay, so with a line pattern, we're going back 20 years into the past, right? So with a line pattern where you would have a grating like that, you would obtain a resolution that can be enhanced along this grating. And in order to obtain an isotropic resolution, you would do what? You would rotate this grating like 3 times, 5 times, 10 times, any times. And you would then reconstruct the image that is inside the petals of this flower, and you would obtain a resolution of about 120 nanometers over there. Now, that is very good news, and that is what the first generation SIM instruments all did. But it's bad news as well, because you have to scan the same image 3 times. So it takes a long time, and you put a lot of burden onto your sample. So you have to illuminate everything with 3 times more laser power than you needed to. So this is the high frequency in space. This is your grid. These are the Moiré fringes, and from the knowledge of one and the other, you can subtract and you can reduce the other one. Now, wouldn't it be nice if we had some kind of pattern that would be modulating stuff in X, Y, in that direction and in different angles all at the same time? And that is the idea of the lattice pattern, the lattice illumination of Eric Betzig, right? Where you would take not a sequence of line, but a sequence of dots. And a sequence of dots projected like that similarly makes Moiré fringes in one direction and in the other direction at the same time. So now with one pass, instead of 3, 5, 10, in one pass, I get all the information I need. So that is a very, very economical, very, very fast way to produce the same result. Yeah? So the petals look a little bit different now. They're not organized in this hexagonal form. They are more diamond shaped, like that. And here you see the raw data on the left side, what this, this is the final image. It's on these booklets. You see here, that's the illumination pattern. You see it's not lines anymore, it's now dots. And you can scan these dots over the sample and then recalculate the image and produce an image that is represented on the right side. And then you validate that. You take little Gata quant nano rulers, and Nanorolers are oligonucleotides with a known sequence, with a known distance between one end and the other end, and to one end they attach one dye, and to the other end they attach a dye. And they know it's 120 nanometers apart, 120 nanometers plus minus 2 or something like that apart, and you can run that under the microscope and you find, okay, at any kind of given angle, you measure the distance between them, you will always retrieve the 120 nanometers. So, from the perspective of the instrument, what do you need? You need a series of gratings. The gratings need to be adapted for the different wavelengths, for the different objectives that I'm using. I need lasers, I need some filters, I need a little bit of optics, but that is in essence all I need inside the ELIRA head. And I need a camera, of course, and I need objectives, and I need the microscope per se, and incubation chambers and whatnot. But optically, I need a grating, a laser, a camera, and an objective. Am I limited to certain dyes? No. You're limited to the dyes for which you're limited to the dyes for which you have, or yeah, it's turned on.
Let me check it, see if it's in sync.
Help me.
I'll try it.
If I press this. No. Wait, it's coming to its senses. Okay. What's there? What's not there? We have to just try this presentation again. Remove this. I have to hurry up, right? We're coming to the end. Bear with me, please. Okay. So you're limited to the filters you have, and whoa, you have dual camera detection, which is another cool thing about the ELIRA instrument. This is how it looks like, by the way. And what can you do with that? You can acquire very quickly two-color images, and then come on. Okay. This is what you see here. I will try to start the movies, the left and the right movies. I will try to start them simultaneously. And the movie on the left is the old ELIRA way, where you would have to, rotate the gratings and everything. And the movie on the right side is the new ELIRA with the faster scanning capabilities. So, here. There. Should start the movies. Like that. Press this button stronger. maybe the next slide will work. Yeah. Oh. There you can see individual vesicles. You have Rab5 endosomes in Golgi in Golgi vesicles in red. This is not very well visible on this image, so that's why I prefer to take a look at one detail that was happening over this entire screen. These little blobs over there. That's what we will be trying to look at. And here's the story. This scale bar down there is 120 nanometers. And take a look at these guys. You go. This really doesn't project very well here. I would like to show it to you on the real workstation up there. Here's another example. This is endoplasmatic reticulum. The green is the mitochondria. You see all kinds of things happening there. You see, this is 255 frames a second. This is actually slowed down. This is in extreme slow motion. What you see there is the ER reorganizing, and here you see this. There's plenty of, each mitochondrion has its own story, the way it's looking for. There's one that is dividing up here. There's another one that is separating down there. There's this one that is like a ring structure. I would like to take a look into this in more detail. So I have the next image like this one. This is one detail from the previous slide. You see here the motion of these particles. Endoplasmatic reticulum. I think this is a very, very sweet little movie.
It's 2D real-time or 3D?
This is in 2D. My computer is already giving up with 2D fast sequences. If I had 3D images here, we would not be able to take a look. But at the workstation upstairs, we can take a look at 3D images. Yeah. So okay. So that was SIM, and we move now rapidly, and then we wrap it up into the universe of. Of course, yes. Improvement in resolution, you get exactly 0. The advantage is you can use 2 times less laser power, and you are about 200 times faster. So far we are using for pixels. What the hell we are using this power? It's already fixed. Sorry? The set's already fixed. It's pixels. Yeah. So what is the benefit to decrease the power? Well, the benefit to decrease the power is, your sample will bleach less over time, or you can use the same power and decrease the time and acquire the 75 micron Z stack you saw in the beginning, fixed that cell. Yeah, that took about 4 minutes to collect. If you collected the same kind of image with a conventional line scan, it would take like 3 hours or so. So it reduces the time and the burden on the sample. There is not much improvement in resolution. Yes. The time resolution 255 frames per second. So it's about, I don't know. To reconstruct it, or to acquire it. So it will take about 15 milliseconds to collect one image. Yeah, 15 milliseconds. About. Okay. the localization microscopy. The localization microscopy is based on the assumption that I can localize the center of a Gaussian with a higher precision, the green curve, then I can resolve it. This is an old concept that you know everyone that is navigating into a harbor in the morning or in the night, when there are clouds or something like that, you will need a lighthouse somewhere, and you can pinpoint the direction of the lighthouse much better than you can resolve its silhouette against a cloudy, a foggy horizon. So pinpointing something, you can do it with a much higher accuracy than you can resolve it. And if you then collect, to stay with the example of the lighthouse, right? If you'd have a lighthouse with many different lamps and you would turn on all the lamps individually, you would be able to pinpoint every lamp, and then you would write them down on a piece of paper, and then you would be able to reconstruct, even though you can't resolve it, but because you could pinpoint them individually, you could resolve the silhouette of the lighthouse and to do this, I decided, okay, how good are we at pinpointing things? And I would ask, 5 volunteers or so to come down here, and we will try to do single molecule localization microscopy like it was done in the initial days. So I need 5 volunteers. Doug, will you volunteer?
It doesn't sound like I'm volunteering.
I'll be also a volunteer. Okay, I'll put a little piece of paper over here. Okay, Dr. Richardson, try to pinpoint this molecule as good and accurate as you can. Doug Fishkind. I will also try to pinpoint it as accurately as I can. The big red one, the big red blob there in the middle. Try to find its center of mass. Right. Thank you. Any more volunteers? Yes. Ah. Applause. Okay. Now we have pinpointed that. And now I will switch that one off and turn on the next one. Okay, there is the next one. Now, please, the next volunteer. Now, instead of making little dots, make a cross. Okay, thank you. I will also make a cross. More volunteers? Okay, yes? Okay, thank you. Okay, so is that it, Andres? You have to do this, since you are actually doing localization microscopy experiments in your real life. Are you crazy? There's no way the molecule is over there. Okay, we'll see. Thank you. All right, so I will now make a little circle around the crosses, which are here, and they are slightly weighted towards these two that are more in the center. And here are the dots. I will collect them over there. Can you see the circle? And now I will tell the computer to figure out the positions of these two objects. And yeah, it's pretty. The computer is pretty good. It's almost as good as we are. And this is exactly what the fitting algorithm is doing. It's pinpointing the positions multiple times and computing the error and the standard deviation of this thing and figuring out, how far can they be apart. And then the question is, how far are they apart? And if I add the little scale bar there, yeah, they're about 50 nanometers apart from each other. So we are able, without the aid of computers, just by pinpointing stuff on a monitor on the screen, to achieve 50 nanometer resolution. Okay, all we have to do now is do this for 5 million or so molecules. Yeah, we will spend the entire next half semester pinpointing individual molecules, or we can ask a program to do this for us. So what does the program need? The program needs to be able to detect single molecules. It needs appropriate sampling. It needs a high signal to noise. It needs appropriate pattern recognition masks. I will not bore you with all these details, but this is all in place. This is all known. The math is known. We know how precise we can measure the things. And we can compute these things, and we can output for a given molecule here. This was molecule number 8. It appeared in frame number 5. Was at position 2155.1 nanometers in X. And we pinpointed that one with 6.2 nanometers accuracy. That were how many photons were in there. That's the background variance and so forth. We all plug it into this equation in there, and we get the precision for this one molecule. And we repeat that for 5 million other molecules. And then we talk about resolution. Suddenly, one thing becomes very, 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 very important. And this is one of the single most neglected aspects of all of microscopy. Size matters. Okay? So what I'm pinpointing is a centroid of a synthetic dye molecule that is about this size, that is somehow on the arm of the 5 nanometer large arm of an antibody that itself is like 20 nanometers in size. So if one molecule is here, the next, and I can pinpoint it with 5 nanometers accuracy, the next molecule will be like 20 nanometers in that direction. Right? So between this molecule and the other molecule, maybe there isn't another molecule. So things will look discontinuous. And that is, if I take a close look here at this microtubule here, you see that there are gaps. And where do these gaps come from? Well, there wasn't a molecule there. Right? Give you a different example. Here, this is the nuclear pore complex. So what you see here, this yellow blob is a nucleus, and each one of these little yellow blobs is a nuclear pore complex. And I can make the molecules switch on and off and pinpoint individual molecules, and that's the image I get. And then I can take a look at this one particular assembly here of individual molecules. There was one here, another one there, another one there, another one here, another. Here is none, there is none, there is none. There's always a gap, right? If I take a look, there are pairs and a gap, pair, gap, pair, gap, pair, gap. I can do this analysis statistically over all the nuclear pores that are in the cell, and I will always find, well, there seems to be a gap over here. So what is this gap? Well, it's maybe the way that the proteins are organized. It's a dimer of some subunit or something like that, where the fluorophores are close to each other in that way. And they're not close to the other side of it. Right? So with the possibility to look at individual molecules, you start to appreciate that level of detail. Right? Things are not continuous. Right? Give you another example here. Tubulin, right? With statistically stained with a red and with a green marker. You will find that where there is a green marker, there is never a red marker. Where there's a green marker, there is not a red marker. Where there's a red marker, there is not a green marker. There isn't any colocalization ever. Colocalization at that level does not exist, as it shouldn't, right? I have a molecule here, the next molecule is not going to be here. It's going to be somewhere else. Okay, to finish it off, you can do all of this also in 3D by encoding some special form into the point spread function of the molecules. I will not bore you with these details, but you can pinpoint not only its position in XY, but also its altitude with respect to the focal plane. And with that, you can reconstruct the images in 3D. This is tubulin network again. Here you have that's where the nucleus is. The nucleus is actually going up like that. And the yellow ones are the ones that are crawling up towards around the nucleus. The blue ones are the ones that are crawling underneath the nucleus. Yeah, or to give you a different impression of the same thing, yeah, you have here the red molecules here, like those, or this one, these red fibers. They are about 1.2 microns above towards you, and the blue ones are at 0 nanometers here with the focal plane. So you can take a look at all these levels of detail. It's not easy, okay? It's easy once it works, okay? But it takes a lot of work to get there, as Andreas knows, right? But once you get to that level, the story you can tell is a very, very beautiful one. I will leave you with one last nice little example. These are two centrioles. The centrioles are like oriented perpendicular to each other, and if you rotate it, you can see the one centriole through the other one. It takes a little while to render all this.
How high is this?
About 2 microns. About 1.4 or so microns is the height. The localization precision there is about 80 nanometer, 80. Okay, the final bit of information is why is this thing called Lyra? If you look at all the Zeiss products, they're all called LSM, Axio something. Why is this thing called Lyra? Well, the story is that there is a star at the constellation of Lyra, the Epsilon Lyra star, which is right next to Vega over here, which, if you look at it, it's not a simple star. It's actually a doublet of doublets. It's actually 4 stars that are about 7 or so light years apart, right? And it's used commonly in telescopes as the gold standard for the resolution of a telescope. So a telescope that is really good will resolve 4 stars. A telescope that is meh will resolve only 2 of them. And the telescope that is not very good will not resolve the 2 at all. So in analogy to this resolution test for telescopes, the name of the instrument was then Lyra. And this is it, seen from the outside, and it's coming soon to an HCDI near you. Thank you very much. Compared to the Lyra where you would have 1 frame per second. But the older Lyra, the one where you go with 1 frame grating, you would have, give or take, 1 frame per second. Yes. 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 Well, okay, no. You are actually sacrificing a little bit of resolution in the shorter wavelength. So you're not going down to 120, but you're going to 130. No, for green. 120 is at 488 excitation. With the 63x 1.4 objective. There are different objectives. There is a special 1.57 NA objective that can boost that a little bit further. If you're imaging with 405 nanometers, you get an extra boost right there as well. But that's not what we call it. That's not. Your mileage may vary. And in the vast majority of researchers are measuring things like GFP, Alexa 488. That's right in the center of the visible field, so that's what we quote. That's something that is easy to test. All the Lyras can be tested with that. And we leave less to instrument variability. That's why the 120 is the... And it's not a solid mark. Some days you can get like 115.
So you showed like a bunch of images in 2D. There's this drug Resolvable that like starts to top out like 2 different structures. Just when you were showing like the images where there was space in between, like what would you do if you were trying to resolve an image of like a microtubule that had been like chopped up that like should have larger spaces.
That is a very, very interesting question, and that I've come across this question innumerable times. So you go to a place where somebody is using this instrument for the first time, right? They want to see the tubule, and they have this impression, well, it has to look like the tubule in the textbook, like a solid line from left to right. And suddenly the thing is like, I have a cluster of 5 over here, then there is a gap, and there are 15 others over there, and then there is a gap. What has happened there? Is that fiber really discontinuous? Is it broken? Is it 2 fibers that did not polymerize together? Or is it a fiber that has another glob around it and the antibody just didn't touch it? Or the GFP that was there photo-bleached, or it didn't fold correctly? It's just not, the lamp is there, but you can't turn it on. Or didn't I wait long enough? So out of all these things that can happen to your molecules, you will never know for sure what happened there, unless you wait infinitely long. And usually you don't have that much time. What you can do, however, and that goes back to your question, is do a statistical analysis and saying, well, okay, is there anything periodic about this? Is every tubulin fiber in my cell, that there is no reason for it to have a periodicity, to have like every gap is 15 nanometer in size? That would, go like, okay, fine. If this is haphazard molecules appearing and disappearing, some of them will be 5, some of them will be 65, some of them will be, it has to be a distribution of sorts, right? But you find that every gap is 15 nanometers in size. Well, that's when you start to get suspicious that there might be actually some kind of 15 nanometer sized cluster in clouding and shrouding that part and is not accessible to you. And so on. You would have to take a statistical assessment of the situation. Try different conditions. It could be longer, I don't know. Cool, thanks a lot.